Hello and welcome to this video. In this video we'll be looking at the graphs of sine, cosine and tan and the transformation of these graphs. Now there shouldn't be any surprises to you with regard to transformation of graphs. This is just a review of chapter 4. So if you haven't watched chapter 4, please do that. It's essential that you already know the transformation of graphs. But and if you find my explanations too boring and you already know them, you're more than welcome to fast forward to the next section and just do the exercises. So here we go. The sine, cosine, tan graphs you should be familiar with. You do need to remember them by heart, as some would say. So the sine curve will always start at 0, 0 from the origin and go reach its maximum at 90 degrees and come back to 0 at 180 and so on and so forth. Make a sketch of this, just try to remember it. And also the negative part is important as well. So make a sketch of the negative part. It's a sine curve, it will just repeat itself on the left hand side. Alright, you can it will repeat itself every 360 degrees. So you could think that point there at 360 is being moved down to 0 and so on. So you would repeat the curve. Now cos, the point to remember about the cos curve is that at 0 degrees it already has a value of 1. So it would have a y-intercept of 1 and it would look like so. Another point about the cos curve that you need to remember is reflected in the y-axis, so it's symmetric around the origin and it's symmetric around y-axis. Alright, so and finally the tan curve has it has vertical asymptotes at 90 degree, 270 degree and minus 90 degree and minus 270 degrees. So these lines I'm putting in here are called vertical asymptotes. It means that the graph will never touch them. It will be tangent to them, but well, not tangent, but you'll get close to them, but not touch them. All right, and there is no values because you cannot type a 90 degree here in this function. Your calculator tell you tan of 90 degree is non-existent. You're asking me absurd question, and tan of negative 90 doesn't exist, and so on, because of the vertical asymptotes. All right, so make sure you remember the vertical asymptotes are, and remember that tan repeats itself every 180 degrees. So the value here is, if we go 180 degrees forward, it, that y value is the same as that y value there. So it's important you remember it repeats itself no matter what. Always just add or subtracting 180 degrees to the angle. You will leave tan unchanged. All right, so now here's the example questions here. You've been asked to sketch them and figure out without using a calculator if you know tan theta is root 3 and so on and so forth. I'm not going to do the exercise for you. I'm going to explain to you what the transformational graphs are. If you remember, this is the summary of what I taught you in chapter 4. Inside the bracket affects the input inversely. If the change is outside of the bracket, it affects the output ordinarily. Here are the summary of what I would say. I'm not going to read them to you, just read them yourself. So, look, here is a reflection. If it's not clear, the negative sign is inside of the bracket. So the original red curve is f of x. What's the shape of the graph for f of minus x? It would be a reflection in y-axis, okay? It's a left and right, okay? Left side of the graph flips to the right around y-axis, and the right side flips to left, and so Okay. Now, if the minus sign is outside of the bracket, it will flip from up down and down to up. All right. So then you have translations here. First, we're looking at the bottom of the page here. So a is added on the outside of the function. So it's a vertical translation. It affects the output, y values shift up ordinarily. Alright, now once again, here is subtracting a value from a function, so it will shift down by a values of a. We don't know what the a is, but it will, if it's added, is outside, moves up. If it's subtracted outside, it moves down. Now here, the a is added, alright, constant a is added inside of the function, so it would translate the graph in an inverse value that you would think. So you, I say you would think, I'm sorry, it's just counterintuitive, alright? So I'm not insulting your intelligence, I'm sure you're intelligent people, so I'm just saying that when a is added, alright, if a is positive here and we're adding a positive value to x value, it will shift the graph to the left. And if you subtract the positive value inside of the bracket, it will shift it to the right. And alright, so if you don't know my explanations, I've tried to show you why that is in chapter 4. Please go back and watch my videos from chapter 4 for. Alright, so once again, I'm very quickly going through the sphere. Outside of the function stretches the graph in y direction, and a value inside of the function actually affects the gradient of the graph. So if you think there is a half in front of the x inside of the function, it will actually double the original y values, and if it's a value of 2, actually halves the x values. All right, so just uh, this is just what I went through in chapter 4, so that's why I'm not talking too much about it. I'm not explaining too much. The point is, we just see the effects on sine curves and cosine curves in a minute. So what in this case here, notice the graph when we put a 2 inside of the bracket, the point where it has y-intercept is fixed on the y-axis. Notice that point is fixed. It will just uh, make the x values closer to the y-axis. It would half them. The fact that we put a 2 in front of the x, actually this whatever this root of the function is, it will be halved. Alright, its value was a -6, is now as -3, and so on and so forth. That 2 is now 1. Okay, so and let's look at this on the sine and cosine curve. So these effects, what does this negative in front of the sine curve do to the curve? Well, y values will flip. All right. So when y values flip, it will look something like so. Okay, graph is reflected in the x-axis. Now, there's a funny thing about sine curve, that if you actually put a minus sign in front inside the bracket as well, x values will flip, all right? But if because the x values of the curve were like so, at here was at minus 90. So if I flip that, if I flip this graph left to right, what you notice is that it will look like uh, this graph. So these two graphs are actually going to be exactly the same. Watch. So it, you see that really, I flipped the x values here, and it looks like exactly the same as flipping the y values, because sine is called an odd function. Odd functions are symmetric, like if it's as if you you rotate them by 180 degree around the origin. All right, so Now looking at the cosine curve, we have a minus sign on the outside of the function. So that means what? It means the y values will flip, so its reflection in the x-axis, and it will look something like so. And but now, if you put a minus sign in front of the inside the bracket, then actually the original graph looks something like so. I'm drawing the left side of the graph as well for you to know. That's just the original cosine curve, right? It will flip left to right, putting the negative sign in front of the angle here. It will flip left to right, but you wouldn't notice any difference. All right, so that's why cos you might want to remember this identity. Cos of theta is the same as cos of minus theta. It might help you solve some problems in chapter 10 when we find multiple angles. So transformation here is addition outside of the bracket. So we added 1 to the sine function. It will shift it up or translate it up by 1 unit. And if we subtract 2 from sine, it's the same as having minus 2 plus sine. So that would translate it by 2 units. Okay, and here we are looking at an inside the bracket. Now I tried explaining this before. Imagine what it does is that you're adding 90 degree. You are moving this y-axis 90 degree forward. Okay, so x, the origin here, is now going to be here. Now imagine the graph is fixed there, and when you're adding something, it's like you're setting up forward the x-axis and y-axis, the frame. Yeah, remember I showed you, like, if you move forward the frame of a YouTube video or my videos, is you're moving the frame. The video stays there where it is. You're moving the frame forward. So we're shifting the frame forward. So what you notice with the naked eye, we would just notice that the graph was moved 90 degrees back to if it was original. All right, originally. All right. So do you understand why that is inverse? To we adding a positive 90 inside the bracket, but the graph moves back 90 to the left. All right. So that's how it is. And if you take away 30 from the original 30 degrees from inside of the function here, so that's like, if I erase everything, it's not there. All right, so that's moving the y-axis back 30 degrees. So the graph, original graph, remains where it is. So we're just moving the y-axis 30 degrees back. So it's as if the graph has moved 30 degrees to the right. Okay, that would that's what it would look like. All right. So just remember that. Here I'm trying to explain one more time the original, uh, like, that's like moving the axis forward by 90 degrees when it's inside the function, and so on and so forth. Okay, so a stretch factor. We have a 2 theta here inside of the function, inside of the bracket, so it will make the graph steeper. Well, what does it mean steeper? Where it reached its maximum 1 at 90 degrees, now it will reach its maximum at 45 degrees. It would be twice as steep, alright? So and then this graph will go there, and when it reached its a low, like, zero value at 180, will be now at 90 degrees. All right, because we are doubling the angle. All right, so it will have twice as many periods as it originally had. We had one period in 360 degree. Now we see two periods. Okay, so go ahead and learn how to sketch graphs for trigonometric functions, with scale factor of a third inside of the bracket. It will actually stretch it outwards. So this original 90 degree, will be three times more out. All right, so what's 90 times 3? 270. So it would actually take 270 for the sine curve to reach its maximum if the angle was divided by 3. All right, so I'm sketching angle of that angle there. All right, uh, sine of theta over 3 on the original graph. This maximum would now move three times further to the right. And the same is true for, all right, the negative values as well. So you see it reaches maximum. So it would take three times as 360 to make a full turn. Notice this is now 360 times 3. This 1080, all right, and this is 180 times 3. 180 times 3 is 540, and so on and so forth. This is 270 times by 3. Alright, I know, yes, it was a division by 3 here, and we actually, the x values will be stretched out by. So we've got two more examples to look at. Let's focus. These are the questions that you uh, so let's read this question. We've been given a graph of a sine curve, transformed sine curve here, where we don't know value of k, and we've been asked to figure it out from the graph. Well, we, from our knowledge of the sine curve, we know the original sine curve reaches its maximum at 90 degrees, and the maximum of the sine curve is 1. So y value would have been 1 and is now 1.5 instead of 1. So the fact that this k is outside of the function, all right, this is telling us this is a affects the y value, or affects the curve in y direction, okay, and the y values have changed, and that k value is must be a half. All right, so we've added half in y direction to the curve, so k is half, or 0.5. Then in the next part of the question, we've been asked to, we've been told that uh, the smallest, what is the smallest positive value of theta that gives a minimum point? All right, so minimum point is at 270 degrees, right? And that doesn't change. The fact that this k is added in the y direction doesn't change the graph in x direction. So its minimum was originally 270 degree, and occurs now when the input is still at 270 degree. What is the value of sine at this point? So what it's saying is that evaluate sine curve at 270 degree. So we know that the graph, the function now has a half added to it at the end. So this was originally at -1. Now we're adding a half to it, so it will be at minus a half. It's not surprising to see that the y value here is minus a half. All right. So that's the end of this example here. You just have to use your knowledge of the sine and cosine curve. Now in this next question, we've been given the changed value, or rather transformed graph for cosine, where k is added inside of the function. So we've been asked to figure out what is the value of k. Now we know that from the original cosine curve, it would have reached its minimum, or sorry, its zero, where here is made a full turn, 360 degree. This is would have been 180 and 90 degree. So cosine of theta without transformation would have been at 90 here. Now that 90 has moved back by how many units? 90 degree. The difference is 20 degrees. Yeah. So this moving to the left actually is where the k value is positive 20. All right. So if you add 20 to the left, sorry, add 20 inside of the bracket, it's as if the graph, the x and y axis moved 20 degrees to the right, and the graph has moved 20 degrees to the left if you think about it. So that k is 20 plus 20 there. All right. So you just have to think about graph transformations, and next we are asked to figure out what's the value of theta at x. X is the other point when it was at the y value is 0. So originally that was 270. Now what we're saying is that 270 was here. Now what is this? Well, this this is a 20 that you would say 270 is the result of what value will give me x plus 20 is 270. So x is 250. Okay, so that's the answer to part B. And part C is asking us what are the coordinates of the minimum. So the minimum, by minimum they mean when the graph is at -1. Alright, so it was originally 180, and because we saying what, let's call this a different letter. This z plus this angle z plus 20 is the same as the cos of z plus 20 is the same as must be cos of the same as cos of 180, which is -1. So you just take cos inverse of both sides. Z is 180 minus 20, which is 160. And everything is moved to the left. You can see we are subtracting 20 from all every degree that we had. So now the answer, it will reach its minimum at 160 degrees. Okay, and well, they've written it here. We've written it here as a coordinate. So the next part of the question, last part, is saying what is the value of this cos of theta plus k where it crosses the y-axis. Alright, so let me get rid of my writing here for the previous part. So we know the value of k is 20, alright, and we are basically saying what's the y-intercept here? But that's what the question is asking. When does it cross the y-axis means what is the y-intercept? So you write this question like so. You say cos of 20, because we figured out the k was 20, is equals to cos of well, this theta we know what is it on the y-axis. This is 0. So basically we're just evaluating cos of 20 degrees. All right, you put that on your calculator and you figure out that the cos of 20 degree when theta is 0 is simply 0.94 to 2 decimal places. Alright, I hope you found this helpful. Good luck practicing. I'll see you in the next few videos.